Hello everyone, welcome to the second video of Quantum Field Theory 2. In today's video, we will be doing second quantization through the canonical quantization method. In this method, we will be building operators out of our field and the field conjugate, which will allow us to actually build particle states. So this is probably the most important video so far in this series, so let's get into it. So a good way to actually motivate second quantization in quantum field theory would to be looking back at quantum mechanics. So in quantum mechanics, to actually do some quantum stuff, what we usually do is we use the commutation relations between position and momentum. So we define the commutator of x in p to be IH bar, and from that causes the position and the momentum to become operators, which act on state vectors, and from that we can actually derive the Schrodinger equation. Now we can also use the path integral in quantum mechanics to quantize stuff. When I say quantize here, I mean like to make it something quantum mechanical. So we can also do an alternative way in quantizing things in quantum mechanics. We can use the path integral instead of using these commutators. But the path integral isn't very useful in quantum mechanics, so we don't really use it that much. But it does have its application. Its real power is in quantum field theory, but in quantum mechanics, it has some applications, but it's not very useful. So in quantum field theory, we are pretty much inspired by quantum mechanics. We can try to do a similar thing to actually quantize our system. Because in quantum mechanics, our system they consisted of particles, right? It's a particle theory. And in quantum field theory, like the main quantity of interest is our fields instead. So instead of setting x and p, the commutator, to be IH bar, we would instead set the commutator of our field, phi, and our field conjugate, pi, to be I. You can see the connection here. And instead of an H bar, we're going to use a delta distribution. Now, this pi over here isn't the 3.14 pi. It's what's called the momentum conjugate. So it's not like the number pi, right? We talked about it quite a bit in our video on gauge theory, or some video on gauge theory, one of those gauge theory videos. And the field conjugate, it's just defined as the time derivative of our field phi. And we call this field, this pi field, the field momentum conjugate, because it's a conserved quantity when we have a field shift symmetry of the Lagrangian. That's kind of like how momentum is a conserved quantity when we have a spatial translation symmetry. So the field shift is very similar to how momentum acts, like in quantum mechanics and just classical mechanics. So this motivates the reason why we see this momentum field conjugate in this commutator. So basically, the field phi takes the role of x, and the field momentum conjugate pi takes the role of our momentum p. So that just kind of motivates why we actually have this commutator over here. So technically speaking, when we use this commutator, we were actually defining our theory, really. Like, we can't really derive this commutator in quantum field theory, right? Because if you stick to classical fields, which we have been sticking with in the past, this doesn't make any sense, right? In the same way, like in classical mechanics, the commutator of x and p is just going to be 0, right? We can't really derive this commutator being IH bar in quantum mechanics, because that's what we define it. That's how we actually start off. That's a postulate, an assumption of quantum mechanics. So we can't really derive this commutator, right? We just really define the commutator in hopes of making the field and the field conjugate become operators. Another way to quantize quantum field theory is use a path integral, but again, we're not going to use that because it's going to be the path integral in quantum field theory has a lot of applications. So like I don't want to come off as saying that the path integral is obsolete. It's very great on dealing with non-perturbative phenomena, but when starting out in quantum field theory, for most of the calculations that we want to do, the path integral is going to overcomplicate things. So we are going to ignore the path integral way for now. So if you guys don't know what this means, that's fine. Just ignore it. So here is the field and the conjugate of the field. We get this by solving the Klein-Gordon equation, which we have already done like 5 times, or probably 1 billion times so far. In quantum field theory 1, we've used this equation a lot, to the point where you guys probably already memorized it. Here, that is a bit different. We have the field conjugate. All we do is take the time derivative of phi, and we just get that. And then, again, our postulate in quantum field theory is this commutator over here. Also, I probably should have specified, for those that may not know, the commutator between any two variables a and b is just a times b minus b times a. That's what the commutator means. So, yeah. Like, if we were to actually write out this commutator, and we were to expand phi and pi, right? If we were to expand phi and pi in these more like expanded terms, and we run the math, we crank out the math, we will actually end up with these 3 relations over here. So basically what we're saying here is that if this is true, if the fields in the field conjugate act this way, then it is a requirement that we have these commutational relations with our a of k and a conjugate k. An alternative way to define a quantum field theory is to start off with these relations over here and then derive this one. So we could work in either order. Most people like to start off with this one and then derive these relations over here, since it kind of feels more axiomatic, I would kind of say. But it is more practical to actually work with these 3 and then go to this first form. So these commutators that you see are really important since we are going to be using them a lot. And from these commutators, hopefully, a of k and a conjugate k will become operators, hopefully. And so will phi of x mu and pi of y mu, hopefully. Again, we are following the intuition of quantum mechanics. They became operators in quantum mechanics, so maybe they'll become operators in field theory. Let's see. So our first contender is going to be the momentum. So in Noether's theorem, we found out that this quantity is the conserved quantity under spatial translation symmetries, right? And if we were to actually expand the stress energy tensor, we would get that this quantity that you see over here is going to be conserved under spatial translations, right? And in quantum mechanics, that quantity was momentum. So in field theory, we also call this quantity momentum. Well, spoiler, it's going to be the momentum operator, technically speaking. But in quantum field theory, this quantity that's under the pink is going to be the conserved quantity under a spatial translational symmetry. So over here, we just have a constant ki that we're scaling the conserved quantity by, because like if we have q being a conserved quantity, we can scale q by any factor and we get a new conserved quantity. So that's where like the k kind of comes in. And the ki is pretty suggestive since it's going to be the momentum, but that's just kind of spoiling the surprise there. But we just add this constant in there for like future reference. So let's actually do some like real physics now. So here's the equation that we have for the momentum operator in quantum field theory. We can see that it contains the A of k numbers. And this is a very important point. So in second quantization, we have that A of k, the commutator of A of k, and A conjugate of k prime is going to be A of k times A conjugate k prime minus A conjugate k prime A of k, which equals 2 pi cubed delta of k minus k prime. So we can immediately see that this A of k, A conjugate k, kind of lines up with this one over here, except that in this case, k equals k prime. So this implies that A of k, A conjugate k, minus A conjugate k, A of k equals 2 pi cubed delta of k minus k, which is just delta of 0. So we can now just say that A of k, A conjugate k, equals 2 pi cubed delta of 0 plus A conjugate k, A of k. And again, this is the exact same, should use the highlighter. This is the exact same thing that we have in here. So we can just substitute the expressions. And that just gives us of ki of A conjugate k, A of k, and then plus, now here is where we substitute this guy in. So plus A conjugate k, A of k. And we can just combine these two terms together to get this. We can then just distribute this integral to get. So now we have this over here. So what we've done is we've used our commutators from second quantization to get this expression right over here. There's no longer a 1/2 term in this first term because these cross cancel with each other. And yeah, we now have this. So we know that delta of x is infinite if x equals 0, and 0 if x is not equal to 0. So this means that this delta of 0 that we see over here is going to equal infinity, meaning that this entire term over here is going to equal infinity. So this means that our momentum operator is just the first term, which is this, plus infinity. Now this is our first divergence that we have encountered in quantum field theory. Yes, our first divergence. It wouldn't be quantum field theory if there were no divergences, right? So this is of course a problem. And this infinity term over here means that basically all particles have an infinite amount of momentum. So since our momentum operator, we haven't shown that it's an operator yet, but it will be an operator. This momentum operator is going to be infinity, meaning that all particles will have an infinite amount of momentum, which they clearly do not, right? This also implies that the vacuum state, the state with no particles, has an infinite amount of momentum, which makes no sense since momentum requires motion and you can't have no particles moving. It doesn't make any sense. So this is a pretty famous problem in quantum field theory. It's more famous for the Hamiltonian, which we'll be covering in the next video. But it's a problem. It's a big problem. And there are a couple ways to sort of get around it. One way is to just pretend that this term does not exist. We completely ignore that second term. It seems like a cop out because it is, right? The argument for the Hamiltonian case is that we can only measure energy differences, but we can't. We could do the same thing for momentum, but what we do here is we just kind of pretend that the second term just doesn't exist, and we'll just see what kind of happens. It's not satisfying, yeah, but let's just see what happens. So if we pretend that the divergent term doesn't exist, we now have this over here. So here is our new momentum operator for the case where we don't have any divergences. So it looks pretty nice until you notice that, oh, we still have a divergence, because if we integrate over all momenta, this integral will likely diverge to infinity. So even if we remove the divergent term, we still have a divergence since we integrate over all momenta. This kind of divergence is called, it has a special name, by the way, which shows you how bad QFT is, that it really classifies the various divergences in the theory. But the name of this divergence is called a UV divergence. Of momentum that's also really large, but traveling in the opposite direction. So some people get confused, like, why do we call it UV if you integrate over very small momentum? Because minus infinity is a very small number, but momentum is a vector, right? So a negative momentum means traveling in the opposite direction. So we're still considering cases where particles have a very extreme momentum traveling in either direction. So because of this looseness, relaxedness, we can have this. It gives us an infinity, so we call it a UV divergence. A solution, a workaround to this, is that we introduce what's called a momentum cutoff, lambda, where we go, okay, our theory probably fails at some sort of momentum scale, or really some sort of energy scale, lambda. So we instead integrate over we integrate over the momentum, but only to a certain point. We stop at that lambda cutoff. And the logic behind this is that our theory probably breaks down at some sort of momentum scale, which corresponds to some sort of energy scale. So sort of like having classical mechanics, it works until some sort of energy scale, the quantum scale. The reasoning here is that at some point our theory will break down, and we can only consider our theory within some sort of momentum range. And we actually call this sort of concept an effective field theory, where our theory is just really a low energy limit, or in some cases a high energy limit, to some sort of larger theory. And this effective field theory approach does make our expressions turn finite. The problem, though, is that our predictions will depend on this lambda cutoff, and we don't really know where that is. So that's a problem with this workaround. The other workaround, let's keep this here. The other workaround is what's called lattice field theory. In lattice field theory, we instead say that space-time is discrete, like on a discrete grid or lattice. So we can only have a certain amount of space-time points. So basically, space-time is no longer continuous, it's now just a grid. And in the lattice approach, this quantization of space-time basically introduces a natural momentum cutoff, which is kind of like effective field theory, but instead we don't use the logic of our theory probably breaks down at a certain point. So the lattice field theory naturally introduces a momentum cutoff, which turns expressions finite as well. So those are the two big approaches out there to sort of solve this divergence, but we won't get into any of them in much detail, and they each have problems of their own to add to the more fun. So yeah, but for now, let's just pretend that like nothing divergent. Let's see where we can go with this. So here is the new momentum operator, the new and improved operator, for the case where we pretend that this guy does not exist over here. This term does not exist. Here is our new momentum operator. So now we're going to take what we've learned to actually describe what these A of k and A conjugate k Fourier coefficients really mean. So first of all, what we've done here is we've just relabeled k to k prime, basically. And you'll see why we actually chose to do this. We're able to relabel things as long as we're consistent, so we changed k to k prime, and then k prime to k. That changes the commutation relation to this over here. Before it was A of k and A conjugate k prime, but we just changed k to k prime and k prime to k. So here is our new and improved momentum operator. What we can do now is we can, like we know from quantum mechanics, that if this momentum operator acts on some state psi and gives us some eigenvalue times psi, then we call psi a momentum eigenstate, where p is the momentum of that state. The same thing occurs in quantum field theory. So what we can do is, well, how do I put this? Like let's try to see what A conjugate k acting on the vacuum state is going to be. So let's see how this A conjugate k acts on the vacuum state. Since remember, we have a commutator involving A conjugate k, which means that A conjugate k might be an operator. So if it's an operator, well then how does it act on the vacuum state? Well, let's actually find out. But first of all, what is the vacuum state? Because the vacuum state isn't really something that we see in quantum mechanics. The vacuum state just represents the state of a system when there are no particles present. So there's no particles, that's what the vacuum is. Some people will tell you that the vacuum actually has virtual particles that popping out of existence. That's not true. The vacuum state has exactly 0 particles in it, because that's how it's defined. Also, we are going to define the vacuum state to be in such a way where A of k acting on the vacuum state gives us 0. Well, how do we know that there even exists some state where A of k acting on that state is 0? We can't really answer that right now, but we'll see the motivation for it in the next video. But for now, we're going to define the vacuum state to be the state where this is satisfied, and where it's a state that has no particles, of course. So with that being said, let's see how the momentum operator acts on A conjugate k acting on the vacuum state. What does that give us? Well, all we have to do is we have to take the momentum operator, which is this, acting on A conjugate k of the vacuum. So what do we do here? Well, we can look at this term over here. Remember that A of k prime a conjugate k equals 2 pi cubed delta k minus k prime plus a conjugate k a of k prime, and that follows from here, right? We're gonna use this property a lot throughout this entire series. It's very annoying, I understand, but we're going to use these commutators to shift our annihilation operators to the right, which will help us get rid of terms that we don't need. So this is a property that we know. So we can just substitute this in for this over here. And that gives us the integral over the momentum 2 pi cubed ai a conjugate k, then times 2 pi cubed delta of k minus k prime plus a conjugate k a of k prime, and then times the vacuum state in the end. So now we can distribute the vacuum state inside of our brackets. That gives us the integral over the momentum over 2 pi cubed ki a conjugate k 2 pi cubed delta k minus k prime times this plus a conjugate k a of k prime times this. Now remember how we said that a of k prime acting on the vacuum state is 0. That's how we kind of define the vacuum state. Well, what we really said is a of k acting on the vacuum state equals 0. But of course, we have a freedom to relabel our indices, which that implies that a of k prime acting on the vacuum state gives us 0, right? And that's exactly what we have over here. So this term is going to be 0. That gives us the integral over the momentum 2 pi cubed ki a conjugate k. Yes, a conjugate k. Actually, oopsie doopsies. Remember that this was a conjugate k prime, right? I forgot to add the prime there. We should have because we have a prime here, right? So we should have a prime here. So we should have a prime. So this should have a prime. This should have a prime. It's kind of hard to keep tracks of all the primes sometimes. So then now we have 2 pi cubed delta k minus k prime acting on the vacuum state. There isn't enough space to put it here. So just note that it's times the vacuum state. These pi's cancel out. We are left with the integral over the k prime. Also, this wasn't clear already. K prime is just some general momentum k prime, and then k is some general momentum k. K could be equal to k prime. K could also not be equal to k prime. There's general values of momentum, and they're generally different, by the way. So now we have ki a conjugate k prime delta k minus k prime times the vacuum state. We know from properties of the delta function that if you have the integral of f of x, then delta of x minus a, that's just f of a, right? So this is just going to give us, when we integrate over all momentum, by the way, this is going to just check out a conjugate k, because this was like the x, this was like the, sorry, no. I mean, technically speaking, the delta function is an even function, right? So we could just write this as k prime minus k. Doesn't matter, but this would be the a, this would be the x. So we would just get a conjugate k, and then acting on the vacuum state. So this is kind of like the cool part in this whole thing. We remember that we were kind of afraid that this would diverge since we were integrating over all momentum, but the delta function took care of that integral and just gave us some finite value, that being this over here. And also we can't forget about this little ki over here that still exists. So here is actually our answer to the momentum operator acting on A conjugate K, acting on the vacuum, is just Ki A conjugate K acting on the vacuum. But remember that the momentum operator acting on psi, that if that gives us an eigenvalue times psi, then psi is an eigenstate, right? Well, this whole thing is basically the psi, right? And this is the momentum of that state, which basically means that A conjugate K acting on the vacuum state, it gives us a state psi with momentum K, I. Or yeah, I is of course a 3 momentum. So this is the momentum eigenvalue, and this is the eigenstate. So the A conjugate K acting on the vacuum state gives us another element of our Hilbert space. So since this psi is the momentum eigenstate, we like to use the term 1 subscript k to describe that, since it's one particle with momentum k. So in other words, A conjugate k acting on the vacuum state is just going to give us a state that has momentum k, which we label like as this. Now, technically speaking, right, this state may have two particles with momenta that add up to k. We haven't necessarily ruled that out yet, but let's just kind of like simplify things a bit and say that if our state has momentum k, well then it just has one particle with momentum k. So yeah, this is a very important aspect of quantum field theory, because remember that this A conjugate k was like, it was the term for it is like a Fourier coefficient, which was so like it was in the mode decomposition of our free scalar field. And when it acted on the particle state, we got this state that's a member of the Hilbert space, this momentum eigenstate. So if the Fourier coefficients acting on particle states give us other particle states, maybe the field itself, maybe the field itself acting on the vacuum state can give us some sort of particle state. Maybe, who knows? So here's the free scalar field that solves the Klein-Gordon equation. Remember that we just found out that A conjugate K acting on the vacuum state, which has no particles in it, gives us some state that has one particle with momentum K. So let's see what happens when our field acts on the vacuum state. That's just going to give us, and we have to recall that A of K acting on the vacuum state gives us 0, and A conjugate K acting on the vacuum state gives us the first particle momentum eigenstate. So this is going to go to 0. This is just going to be 1k. So this is just going to give us integral over the momentum. So we get this quantity over here for the field acting on our vacuum state. So the field acting on the vacuum state actually gives us another vector state. Because remember that an integral is just a continuous sum, right? So we're basically just summing over the momenta. So like, we're basically saying that that our field acting on the vacuum state is just like the momentum agitate for when the momentum equals 1, then e to the I x mu. Let's just use x here just to be sloppy. And then like plus 1.5 e to the I 1.5 x plus the momentum agitate that has 2 momentum whatevers e to the I 2x. We're basically summing over all possible momentum eigenstates, and the momentum is continuous, right? It's a continuous sum. And then at the end, we scale up by 1 over 2 pi cubed square root of 2 omega k. So basically, to put it in more like kind of physical terms, we're basically summing over all the possible plane waves, or we're summing over momentum eigenstates that are weighted by the plane waves. And we know for a fact that by summing over all the possible plane waves, we get the delta function. So second quantization tells us that our field is an operator. Because remember that at the start we were saying that, oh, if we set a commutator of phi and pi, like phi and pi will become operators, right? Well, that's exactly what happened. Our field acts on the vacuum state, and it's going to give us a new state. That state, it's going to be a particle state that is at some position x. So our field is now promoted from just being a classical function, a classical field, to now an operator value field, or an operator value distribution, like the mathematicians love to say. So, yeah, our field now is an operator, just like how the momentum operator is an operator, or like how the Hamiltonian is an operator. It's an operator in that sense where it's going to act on the vacuum state, and it's going to give us some new state, this state being the position state. And the reason behind this, like how we know this, is because we are summing over all momenta with the plane wave. And that's exactly what a delta function does. And a delta function is it's the projection of the position state along itself. So this is going to be a state that has the position x. Now, technically speaking, for those that have already studied quantum field theory or are like beyond this point right now, you may know that this is actually a lie. It's not true that the field acting on the vacuum state is a perfect position state, because if we were to project the position state along itself, you would not get a delta function. Instead, you'd get something that is approximately equal to a delta function. So this is technically speaking a lie, but it's a good enough lie for us to use for now. And we'll be proving ourselves that it's not exactly a delta function in like the next video or the next 2 videos from now, when we start talking about propagators. But this just tells us that our field acting on the vacuum state will give us something that is sort of a position state, but not exactly. But for our purposes, it's just going to be a position state. So you guys may have heard the claim that particles are excitations of field. So like say like here's some field, right? A particle would be like some excitation or ripple of the field. That is just pop sci garbage, all right? Particles are not field. Particles are not excitations, not ripples. They're not vibrations of fields. Well, when people say this, they get this idea from what we've just discussed. They get the idea from the fact that our field acting on the vacuum state gives us a particle state that is a position eigenstate. That's where they get the idea of field vibrations, fluctuations from. But what must be understood is that this position eigenstate is not equal to the field. The field is an operator. One is a vector, one is just an operator, right? This ket state isn't some configuration. It isn't some wave packet of the field. A ripple in the field is still a field, right? Because here we're integrating over all momenta. You know, we are considering cases where we do have ripples in fields. A simple ripple in the field is it's still the field, right? It's not a particle. A particle state happens when this operator just acts on the vacuum state. So when people say particles are excitations of fields or they're built from fields, that's not correct. They're being very sloppy in their language. The particle state isn't the particle itself, right? It's a mathematical tool used to calculate probabilities that concern particles. So the field and the state are two different things, all right? Because like I hope I'm making that clear. It probably is already clear to you guys, but I'm just pretty much warning you that you'll hear some people say that, oh, particles are fields. They're not fields. The states are members of a Hilbert space or a Fock space, whereas the fields are operator value distributions that solve the relevance equations of motion. In this case, the Klein-Gordon equation. So they're different things, but basically the field is an operator that acts on this vacuum state, gives us a particle position state. So yeah, we are pretty much done. This is second quantization. Everything that we'll do will be built on this. So this is probably like one of the most important videos in this entire series, since like second quantization, it's really what makes quantum field theory a quantum theory. In the next video, we will be going over the number operator. We'll also be going over some other things. And yeah, so thanks for watching and have a great day. Bye.